the podium as we're ready. He's Gonzalo Gala from the University of Illinois, and he's going to be speaking about the use of surface waves to evaluate in-place strength of concrete. Gonzalo is a PhD candidate at the University of Illinois. He previously had his master's degree from that institution, as well as a BS from the University of San Francisco in Ecuador. So, this should be. Come on, there we go. Thank you.
Thanks. And thank you all for being here. Today I'll be talking about the use of surface waves to characterize in-place strength of concrete slabs, concrete pavement. And this is an ongoing research in the University of Illinois, guided by Professor Popovics and myself. So why do we need to determine the in-place strength of concrete pavements? Well, this is an issue for quality assurance and quality control, because we want to determine if the contractor is doing what he's supposed to do. But we are also willingly decided to know if an existing structure can withstand certain loads. So the common practice right now is to use cores. Cores are fairly a direct measurement of the strength of a pavement. However, they are highly expensive because you need to take a lot of cores. You need a lot of time to do this core testing. And besides that, you're leaving some damage in the concrete that later needs to be patched. And this is a statistical problem too, because you need to take a certain amount of cores in order to have good correlation with your data. So non-destructive tests come out to be a really good and fair approach. And through thickness velocity measurements, UPV can have and can show good results in this. And we saw a presentation earlier today, the first presentation, in which UPV was used to characterize in-place strength of concrete. However, the drawbacks of UPV in this particular case is that you need a two-sided axis, and right now we are dealing with concrete pavements, so we cannot apply this UPV. Therefore, we are looking for a completely non-destructive technique to characterize in-place strength of concrete pavements using a one-sided approach. Our selection was to use surface waves. Why? Well, first of all, they're easy to generate. And besides that, we can have a one-sided approach. This solves the problem that you're facing with UPV. Not only that, but you can take a lot of measurements, and this solves also a statistical problem that you find using cores. And finally, there are multiple parameters which you can use and you can obtain from surface wave velocities and transmission, and they can both be used to correlate with strength. So what are the velocity measurements? If you see the small cartoon to the right, you can feel what we are doing in Illinois right now to get the velocity measurements. We fix two sensors at a distance d, and then we generate an impact close to one of the sensors. This impact generates some surface waves that are then felt by the first sensor, such as is shown in the cartoon to the bottom with the red signal, and then by the next sensor with the blue signal to the bottom of your screen. And since we can tell the time difference between the arrival of these two signals and we have the fixed distance, we can determine the surface wave velocity. We also used UPV to correlate with our data because UPV is so widely used in the field, again, as it was previously explained in another presentation earlier this morning. On going to transmission measurements, we used a self-calibrating technique or a self-calibrated scheme, and the set of equations is here. If you pay attention to the little sketch on the bottom of your screen, you can see that there are 4 locations. Numbers 2 and 3 is where we place the sensors. The spacing that we have been using in the University of Illinois is 5 centimeters. And then on 1 and 4, we generate the impact that causes the surface wave to travel from there to the 2 sensors. So if you look at the frequency domain, you can see that the equations that correlate all this data are already posted up there. And let's take, for instance, the first one, B12. Here you can see that there's an A term, which explains the sending signal response, and then also an S term, which signifies the receiving response. The one that's correlating both of them is D12, and like that we can also relate what's happening to the other sensors. our goal is to isolate the term 2,3, D23, which is the transmission between the two sensors that we have there. So how do we do this? Well, obviously, we can mathematically play with all this set of equations that are valid in the frequency domain and get this value D23, which is a transmission. And from now on, I'll call it the signal transmission. And this is simply the transmission across a region between these two sensors. And it's just the ratio between what is the far sensor is receiving to what the near sensor is receiving. So for instance, let's say that we have a transmission value of 1. This implies that there's a perfect transmission. So what the sensor 2 is receiving is exactly the same as what sensor 1 is receiving. On the other hand, if you have a loss in transmission, then what the sensor 2 is receiving is not the same as what sensor 1 is receiving. There's some scattering, there's some loss of the signal, and that's why the transmission value goes down. Obviously, we want to know that what we're getting between the two sensors and the transmission between these two sensors is exactly the transmission between them, and there's no other factors affecting that. So we have to define some signal coherency or some signal consistency. This defines the usable frequency range that we can apply for our experiments. And you can see here an equation that we use in Illinois, in which we use the average of 5 signals, 5 transmission values between the sensors. The threshold that we have established is 0.99, which is pretty high if you can consider that. And that will imply that, for instance, in this graph over here, the only frequency range that can be used is between 104 to 132 kilohertz. So the rest of the data is discarded in this case. So only that is useful for us, sorry. Transmission, therefore, for the previous case would be between that frequency range that I explained. And what we're looking for is for a flat, clear signal, such as this one. In this case, we limited even more our results to where we had a good coherency and a good response. And the frequency ranges that we ended up using were between 115 to 125 kilohertz. By no means this implies that you cannot use other frequency ranges. These were useful frequency ranges for our particular cases because geometry, the impact source that you have, the sensor that you're having, will all determine the way that you use your frequency ranges. But this came out to be useful for the slabs that we were testing. So what were these slabs? We decided to make several concrete specimens that were 50 centimeters by 50 centimeters by 10 centimeters thick. These slabs were to mock pavement, and that's why we decided to change several parameters. First, we decided to vary water-cement ratio from 0.4 to 0.52, as you can see over there in the table. And we also considered that adding an air entrainer was important because this work is partially funded by the Virginia DOT, and they are usually worried about the use of air entrainment because of the changes in weather. So, as you can see, we had those variations, and the compressive strength was determined by the use of companion cylinders tested at 28 days. However, there are other parameters which can affect compressive strength, and that's why we decided to consider varying the cement content at a fixed water-cement ratio, as you can see in the last table. These slabs were tested at 7, 14, and 28 days, again with compressive tests of companion cylinders. And as you can see, we used 3 mixes. One which had a very low cement content, which we, from now on, I call the lean mix, and one with a really high cement content in comparison to the normal ACI recommendations, and that I will refer to the rich mix. This is the setup that we're using right now. As you can see, we have some companion cylinders and 2 sensors with a fixed spacing of 5 centimeters, which I already told you, and we have an impactor. The impactor here is an automatic impactor, so we can have control over the signal that's being sent. And the miniature accelerometers are then connected to the oscilloscope through some amplifiers, and the signal in the oscilloscope is in the time domain. This signal is then acquired by a computer, which transforms the signal in the time domain into the frequency domain, where the equations that I showed you previously are valid. The computer also takes this signal and calculates the coherency and gives us the transmission values. The program that we are using right now is lab Windows based, and it was also developed by one of my companions in the University of Illinois, and therefore we wanted to verify that this program was working fine. So we went into a steel block, which was completely homogeneous, and before we had already tested to see if there were any cracks or any voids inside it. and it was in perfect condition. So theoretically, the transmission in this steel block, given the setup that we are using, would have to be of 0.71. So we were looking for regions and trying to verify that the signal was exactly like this in the steel block. And to the left, you can see one of the transmission values that we're getting in the steel block, and it's exactly of 0.71 at the high frequency ranges. So we were encouraged at this because the problem was working. So then we decided to go into the concrete slabs that we had designed. As you can see, the compressive strengths do vary with water cement ratios. We were expecting that, and the compressive strength was obviously lower as the water cement ratio went higher, and also those which had air entrainment had lower strengths. With the slabs that had a fixed water cement ratio but varying cement content, the lean mix, which was surprising for us, had a lower strength, and the one that had more cement content had a higher strength. But anyhow, they all showed a trend of increasing strength with time. So how did we decide to approach these data sets? We took several measurements, several NDT measurements, as I told you before, both surface wave velocity measurements and UPV measurements, as well as these transmission data sets. And we tried to correlate this data to predict the compressive strength that we had tested with compounding cylinders. We also tried to variate and combine these data sets. And we used several fits in order to see this trend. So we used linear fits, polynomial fits, and exponential fits. The quality of our measurements was based on this equation that is shown here, which is defined here by ourselves as error, and there is the average of the square errors between the data sets predicted and measured. Now let's look at some of the data that we have gotten. Here we can see the UPV measurements, which are the normal data sets that have been used in the field and what we saw earlier this morning. And as you can see, there is a good coherency and a good trend in the data sets with the compressive strength. So there's some linearity here. However, there is, as you can see, some spread, and this was even shown earlier today, in which a larger number of cores were taken and the spread was even larger. The error here was measured to be 981 psi, and this will be used for comparison later. And the sensitivity is not that good. What I have defined as sensitivity is this variation from the largest compressive strength to the lowest compressive strength related to the parameter that we are using to predict it. And in this case, it's of 20%. So we have mixes that are varying from around 6,000 psi to 1,000 psi, and there's only a 12% difference in the UPV measurements. Looking at same data, but now for the surface wave velocity and transmission data sets, we see that the surface wave velocity has a similar trend to that of the UPV. That is, there's a good correlation with the data. You can almost apply a linear fit, but there's a scarce sensitivity. On the other hand, the transmission values do not show a good correlation. In fact, they have the worst error of 15, 11 psi. However, their sensitivity is the largest. So we wanted to use transmission data because they have the largest sensitivity. And if we can combine those data sets, we could probably improve our results. So how to improve them? One idea that we had at the beginning was to normalize the data sets. By normalizing, we can obviously play around with the data sets, combine them, have different linear fits, different fits to combine, and to try to show a better trend in our data sets. From all the combinations that we applied, we saw that the best ones were with a normalized surface wave velocity raised to the 10th power. By doing that, we were able to increase the sensitivity from 13%, as it was shown before, to 70%. And the linear trend was even improved. The surface wave velocity measurements were normalized by a value of 2,400 meters per second, sorry. And the transmission by this predicted value of 0.71. This table shows the results that we got, combining all the linear and polynomial and exponential fits that we tried, as well as the different data sets. As I already told you, the normalized velocity and normalized velocity to the 10th power show the best results. and UPB also showing some good correlation. The normalized data transmission sets didn't show an improvement, and in fact were the worst. And by changing the fit from linear to a polynomial or even to an exponential, there was some improvement. But however, this improvement is not large if you compare it to what we were getting with a linear fit. And that's why we decided to stay with the linear fit, since there's a less computational effort if you're requiring to change the linear fits that you're using. So it's simpler to combine the data in a linear fit. Also, I want you to notice that combining the data set didn't improve the results. That's what we were looking for at the beginning, since combining the normalized transmission and normalized velocity, the last two data sets on the table, only bring down the error to 1,000 psi, while the normalized velocity still has a much lower value of 700 psi. So, in conclusion, first, the surface wave velocity and the transmission values are useful to determine the compressive strength of concrete. And I think that our scheme of a self-compensating technique is very helpful to determine this transmission value and to determine the compressive strength. Surface wave velocity and transmission do correlate well, and we think that there is further work that can be done with this. The normalized surface wave velocity and the normalized surface wave velocity raised to the 10th power, so even the best correlation fit. And there was a 20% reduction with what is predicted with UPB. That is the normal NDT technique used to correlate with strength. Although there is some variability in the transmission data point, we still think that this can be improved if we can change the data set and the way that we are doing the experiments right now. And if we can combine these transmission values with the surface wave velocity measurements in a multilinear fit or in some other way, we could probably further increase the correlation of these data points. That's why this is still an ongoing research in which we are trying to apply all these measurements and trying to improve them in the future, combining these transmission and velocity measurements in order to gain further sensitivity and still keep a good fit and low error in our measurements. I would like to acknowledge the Virginia Department of Transportation, which is the funding agency for our research. And at the same time, I would like to thank Gonzalo Cetrangulo, who is an intern working in our lab, who has done most of the experimental sets and which has worked with his labs, which you probably know it's really hard to be casting slabs every day and taking measurements and carrying them around. If you can imagine these big 50 by 50 centimeter slabs, they weigh a lot of things. So him and myself have to carry them around, and I really want to thank him for all the work that he has done. Now I would like to entertain some questions.
Thank you. Do we have any questions for Gonzalo? Yeah. Could you please come to the microphone?
What kind of sensors did you use?
That's a good question. We used miniature accelerometers in order to determine the signal, how it was arriving, and they seem to work fairly well. But we have problems, obviously, with coupling. That's something that we try to work in the future. We're thinking of new ideas of how to work with this so that the measurements can be taken faster, easier, and we can overcome.
What was the natural frequency?
The frequency of the accelerometers, it's around 60 to 80 kilohertz. And that's exactly what we are trying to look for to improve this. And one idea that we're having is to work with exponential transducers. I don't know if you have heard about them. But the idea is so we can have less contact and work with particular frequency ranges, exactly the ones what you were looking for.
And what was the distance between your impact location and the sensor?
The distance between the impact and the first sensor is exactly the same as that between the two sensors. So in this particular case, we use a 5 centimeter spacing between sensors. So there's also a 5 centimeter spacing between the impactor and the first sensor. That's why the transmission value comes out to be 0.71, which is the square root of 1/2.
Did you try to do any tests to vary the distance and see what the effect was?
We have tried several distances, and they seem to work fine depending on the geometry that you have. And the work is really much larger than I showed you today, but we tested smaller slabs and larger slabs. There's always a geometry factor here, so if you use a larger spacing and smaller slabs, you begin getting reflexes from the bottom or from the sides. So it's probably a good idea to reduce the distance between sensors, but we have tested it on very large slabs, probably a square meters in size, and we have increased the spacing up to like 10 centimeters, and it seems to work fine, as long as you keep the ratio.
Okay, thank you.
Welcome.
Any other questions, Mike?
Mike Ford, Edinburgh University. Very, very nice presentation. Can you remind us what kind of impactor did you use on this?
It was a mechanical impact. The impactor that you saw over there, it's a German impactor developed by Develogics. And the nice thing about it, it's a consistent solenoid impact ball that strikes the surface of the concrete. And you can get also the signal input. However, you can use any ball. I mean,
Okay, it's just a standard ball bearing from,
Yeah, it's a ball bearing.
from German Instruments.
Yeah.
Yeah. Okay, thank you.
Oh, welcome.
Okay, any other questions? Sure, Pete.
I wondered, in one slide, you showed the companion cylinders for the slabs. Is that what you determined your compressive strength for the slab from those companion cylinders?
Yes, we casted 3 companion cylinders to be tested at each time. So if you recall, for instance, we did compressive strengths at 7, 14, and 28 days. So for each measurement, we had 3 companion cylinders that were tested. And like that, we determined the compressive strength. Exactly on the same day that we did the compressive strength, we took the NDT measurements. So like that, we will have complete correlation with the data.
Okay, and those were laboratory cured in accordance with standard practice?
We follow the standard practice, yes, the ACI recommendations.
Were the slabs cured the same way? Or
The slabs were follow the same.
so they
the
were
same-
moist cured as well?
Exactly the same. We use the moist cure room in the University of Illinois, which is a standard moist cure room, yes.
Did you give any consideration to the possibility of coring these slabs after the fact to see what kind of core compressive strength and any remaining cylinders might have been?
Yes, we're giving consideration to that. We're still making some measurements in the slabs, that's why I cannot core them yet. And they are also 10 centimeter thick slabs, so obviously you have to regulate how you core them.
Right.
Because they are rather small, so you get into a size effect.
Right.
So the companion cylinders, you can make them as the ACI recommends, but obviously if you go as small to this, you have to keep twice the length, twice the diameter ratio, so you end up with really small concrete cores. And there's a size effect over there, so you have to consider that.
Thank you.
Welcome.
Any other questions? Any other questions? All right. Well then, thank you very much. Very nice presentation.